So almost all the practical devices are made of using semiconductor materials. Solar cells are generally PN junction based kind of devices, and these converts light into electrical energy. Photovoltaic technology can be categorized into three main generations: first generation, second generation, and third generation. In the first generation, the solar cells were based on the single crystals or polycrystalline materials, but in the form of wafers. In second generation, solar cells were based on thin film based technologies, and polymer solar cells, bilayer, bulk heterojunction, and nanostructures bulk heterojunction solar cells are comes under the third generation. Dye-synthesized solar cells, perovskite solar cells, quantum dots. All these are the third generation. Now let us see thermoelectricity. What is thermoelectricity? First, so suppose we have a metal piece. So a metal is having free electrons. So there are a lot of free electrons in the material, and they are distributed over the entire metal uniformly. If there's no other external forces applied or electric field is applied, in that case, these electrons are uniformly distributed inside the metal. Now, what happens? Suppose we start heating one end of the this metal. So what will happen? The temperature of this part will rise, and these electrons which are here, they will gain certain thermal energy. And this thermal energy, because of they have got some energy, they can actually try to move towards this side. So suppose over a period of time, temperature gradient is developed. Here temperature is T1, here temperature is T2. And so because of this thermal energy, the electrons will move from one side to another side. So this part will become more negative, and this will be positive. So an EMF will be developed between these two ends. So suppose this is at potential V2, this is at potential V1. So if we see V2 minus V1, there will be a potential. So this is actually the main principle behind the thermoelectricity. So if you apply a temperature gradient across a metal or semiconductor, charge carriers diffuse from one end to another end, and a potential difference built between these two ends. And at a certain stage, this built-in potential start resisting the further diffusion of charges. So suppose these electrons have moved this side, so this will be slightly negative, this portion, and this will become positive. So now even if you are heating with a more heat, this part is provided more, the thermal energy will be still increasing of these electrons, but since there is a net negative charge, net negative potential here, so this built-in potential will try to resist. So after some time, a thermal equilibrium will be established where you will have this end at certain potential and this end at certain potential, which is different than this potential. And so an EMF will be generated. The different. Now this was actually when you have a single material. So suppose you have same material. Now you put like this. You have one rod and you have placed another rod of the same material. So what will happen? You heat this part, and so electrons will go towards this side. Suppose it is having electrons as a charge carriers, and okay, if it is metal, then the electrons will move from this to this part. And so since both these materials are, or both these, you can say, uh, both these rods are identical or made of same material, and therefore exactly same amount of electrons will go from this side to this side, and the exact same amount of potential difference will be generated. So this will also be, suppose in the same example, if I say T1, T2, this will be at V2, and this will also be at V2. So if I measure, you can say this is also at V2, this is also V2. If I try to measure the potential difference between these two ends, it will actually be 0. Now, imagine another situation where one of these rods are made of different material. This is of material, this is of suppose metal A, this is of metal B. So each metal has this different the electrons which move from one side to another side. It depends from metal to metal how many electrons moves and how much potential difference is generated. So in suppose you have two dissimilar materials, obviously the potential V2 and here in metal 1 will be different than to metal 2. So in that case, a net potential difference will be generated between these two ends. Suppose this is one material, this is another material. So when two dissimilar materials are joined at one end and heated to temperature, suppose heat TH, the other end, both metals are kept at the same temperature TC, a potential difference or EMF builds up between these two metals. So here we can see that some potential difference is developed. And this temperature difference can be converted into potential difference. It is obvious. So here it was delta T, so it has correspondingly it has been converted into delta V. And this is called as the this effect is called as the Seebeck effect, where because of the change in temperature, or you can say a temperature gradient, a potential difference is generated. And then this is Seebeck effect. And what is Seebeck coefficient? The ratio of potential difference to the temperature gradient is called as the Seebeck coefficient. So Seebeck coefficient is denoted by S or sometimes alpha, and it is given as potential difference generated per unit value of temperature difference. If temperature difference is more, you simply divide it to get it unit temperature difference potential. Now this was the case when we had two metallic materials, but two dissimilar materials. Now, if the material, both these materials are same, identical, of the same metal, in that case, there will not be any potential difference. So, it will not work as a thermoelectric device. So, we need two different material, two metallic difference material. Now, suppose we have one P-type material and one N-type material, or N-type semiconductor and P-type semiconductor. So in P-type semiconductor, you have holes. In N-type semiconductors, you have electrons. So you will see electrons will move in one side. Similarly, holes will move the same side, and then you will get a you can say double the potential. Now, what is the problem in this situation? Suppose you need to have two dissimilar material in order to measure. But if you want to generate electricity, you need to put one wire here, another wire here. But if you join with P and N type, then you can have a different structure where both the electrodes can be provided at the colder end. Now, the performance of a thermoelectric device depends on the figure of merit. Figure of merit is a parameter for any material, and it is defined as alpha square or S square also, that is Seebeck coefficient, multiplied by sigma, which is the electrical conductivity, divided by the K, that is the thermal conductivity, and multiplied by T. T is the multiplication of T is usually done to so that to make it a dimensionless quantity. So this ZT value is very important value for thermoelectric materials. For commercial applications, you need the materials with the ZT value greater than 2. And for conventional materials, normally the materials which are available, experimental materials which are very commonly used, the ZT value are generally in the range of 1 or near to 1. So a good thermoelectric generator material should have what it should have. It should have more alpha. It should have more sigma. It should have less K. So it should have high Seebeck coefficient, should have high electrical conductivity, and it should have low thermal conductivity. But you know, the electrical conductivity and thermal conductivity are related. The materials which are having higher electrical conductivity are generally having higher thermal conductivity, and vice versa also. If some material is having low electrical conductivity, obviously it will have low thermal conductivity also. So that part has to be taken. How? So special methods are required where the thermal conductivity is manipulated in these divides in order to get a better ZT value. The conversion efficiency of a thermoelectric material which is having figure of merit Z2 is given by this formula. Suppose TH is hot end temperature, TC is cold end temperature. Then the efficiency eta is given by TH minus TC divided by TH, and then square root 1 plus ZT minus 1 square root 1 plus ZT plus TC by TH. And generally, the efficiencies are in the range of 5 to 8%, and good efficiency in thermoelectric materials are in the range of 10%. If you find a material with efficiency or thermoelectric material with an efficiency more than 10%, it is very, very good efficiency. If we see a typical thermoelectric power generator, it is like this. You have a hot end, or you can say where the heat is generated or something is kept at a higher temperature. It could be anything. It could be a engine of a car engine, which is at a very high temperature. And then there's another end, which is a cold end. You can have some normal material at room temperature, or you can have some temperature, some material, some assemblies with some cooling arrangement, like having some heat exchangers or some water flowing arrangement. Yeah. You can have some heat exchangers. So you have a hot end and then you have a cold end, and between those two ends, a thermoelectric generator is placed. And from this thermoelectric generator, you need simple wires where the current can be drawn or power can be drawn, and then you have a load, whatever load is there. Generally, these devices are low voltage and very high current devices. The working of thermoelectric generator is based on Sebec effect. Thermoelectric power generator is a solid state device that converts heat directly into electricity. It consists of a heat source which is kept at a higher temperature and a heat sink which is maintained at the temperature which is less than the heat source. So heat sink can be water cooled, air cooled, or a normal device, not a room temperature device. The temperature difference between heat source and heat sinks causes direct current to flow through the load, as I explained. So now let us see why we need high sigma and poor thermal conductivity. So suppose the thermal conductivity of this material is very good or very high. Electrical conductivity is very good and thermal conductivity is also very good. So if so what will happen if this is not an infinite source of heat, or it is an infinite sink, then what will happen after a certain time, because of the thermal conductivity, the temperature of this will become equal to the temperature of the cold end through this. And therefore, the temperature gradient will cease to exist and there will not be any thermal power generation in that case, or power generation. So that is the reason why you need to have poor poor thermal conductivity, so that the heat flow should be as less as possible. However, the electrical current should be more. If this is just an animation, you have a heat source and you have N-type material and P-type material. In P-type, you have normally holes. In N-type, you have the majority charge carriers electrons. Here, the majority charge carriers holes. You have a heat sink. So now you have put arranged in this way that heat source is connected to both P-type and N-type legs, and then the wire or the connections are electrical connections are drawn in such a way that both are at the connections are at the low temperature. So suppose you have temperature is high, so if that temperature is because of that temperature, these electrons will be moving, same way the holes will be moving, and these will be through an external circuit, they will move and recombine, and then effectively a current will be flowing. So the same picture in this way, you have a hot end, you have a cold end, and that connections are placed from this side through a load. The electrons will flow from this side to this side, holes will from this side to this side, and they will combine, and the current will be flowing through the load. So the power generated due to the Seebeck effect is a single phase DC. So it is obviously it is a DC only. So current is flowing only in one direction, this direction. So electrons are moving from this to this, so current is moving this to this direction. So it is in one direction, it is a DC current. The output voltage and output power are increased either by increasing the temperature difference between the hot end or connecting several thermoelectric power generators in series. So if you want to increase the power, what you can do? You can increase the temperature of hot end, or you can decrease the temperature of cold end. You can do you can provide a refrigeration also here if you wish. So you need to increase the basically temperature difference. One thing is that, and another thing is that now you know some current is flowing. If you have another such device exactly similar, you put it here and then you connect both of them in series, then the voltage will be increased, or if you add both of them in parallel, then current will be doubled. So if you add them in series, the voltage will be doubled, and if you add them in parallel, in that case the current will be doubled. So so you have increased the power by adding, either you can do several thermal generators in series parallel, or by increasing the temperature difference. As we know, the voltage is given by delta T into S or alpha here, where alpha is Seebeck coefficient and delta T is the temperature difference. So all thermoelectric power generator has the same basic configuration as shown in the above figure. This figure, you will have a one N-type, one P-type, and then they will be connected like that. And then there are several such units such legs, they are added in parallel and series to make a bigger power, where the more power is extracted out of the thermoelectric device. So in a thermoelectric cascade device, those devices are called as cascaded devices. You have several legs attached to one to other. So in T cascaded devices, P and N type materials are connected electrically in series and thermally in parallel. So you have, see, this is N type material, this is P type material. So they are, how they are connected? They are connected electrically in series. So this goes like this, and thermally in parallel. So you thermal source is this and sink is this, and thermally they are connected in the parallel. So thermally both are seeing the thermal current in the same direction. It means heat is flowing from this to this in both sides. However, the electrical current is moving from one side to another side like this. In this, it is moving if this way. Then in in hole type, if the current is moving like this way, then in N type, it will move opposite way current. So these are thermally in parallel and electrical in series. Electrically in series. A typical small TE module is this. So there are several such assemblies which are small assembly which are connected to connected in an appropriate way, so that there are several series connected devices, there are several parallel connected devices, and you increase the voltage, you increase the current, and you get the more power. So in a module where which is such bigger thing are called as the module. And these are called as the power generator. Then you have several. So this is a typical module which is commercially available, where you put one end, and then inside this you will see there are several thermoelectric devices which are connected in this kind of assembly. You can have this. This is one configuration. This is another configuration. So one side you put at, this is at hot end, and the lower part you put at the cold end, or vice versa, whichever is convenient. Now, see, all these things depends on the thermoelectric power generator generation depends on the Seebeck coefficient. So if we see for a semiconductor material, the Seebeck coefficient can be defined like 8 pi square m star k square t and 3 eh square, and then pi divided by 3n to the power 2 by 3. What are these? M is effective mass. Effective mass. What is effective mass? That we saw in the second lecture. Effective mass, the same effective mass here also. AB is the Boltzmann constant. T is the absolute temperature. And is the charge. H is Planck's constant. And these are all the constants. So if you need to have good material, the Seebeck coefficient, these parameters, these are basically material dependent parameters. So the transport properties, now electrical and thermal conductivities, if you want to see the electrical conductivity and or electrical resistivity are related to the carrier concentration through carrier mobility by the following equation. This equation we saw in the second lecture also. The conductivity is directly proportional to mu, which is the mobility, and then N is a carrier concentration, and Q is the charge, and it is 1 by the resistivity. Thermal conductivity is the property of material which indicates its ability to conduct heat. Electrical conductivity is the ability to conduct electricity. Similarly, the thermal conductivity is material property which shows how this material is able to conduct heat from one place to another place. And this how, in what way any material can transport heat. Like electrical conductivity, for electrical conduction, it can do only through electron and hole. That is the movement of electrons and hole or charge carriers. However, thermal energy can be transported by any type of excitation in a solid. So in this case, there are mainly two kind of contributors to transport the heat from one place to another. One is electrons and holes, which is transporting heat energy. Because the electrons, when they are moving, they are having certain amount of kinetic energy. Similarly, the holes also. So with that, they take energy from one place to another place, and they can deposit by striking to other electrons at that place where they have reached, or at the lattice also. So one is that when electrons and holes, they transport heat, and another is the phonons. Phonons are, what are phonons? Phonons are lattice vibrations. So that these phonons also they travel through the lattice. Phonons is the quanta of lattice vibration. As for the you can say atomic in the atomic spectrum, you see photon. In the lattice vibration or vibrational spectra, you see the phonons, which transport it and travel to the lattice. So the lattice thermal conductivity, what is that? One is the conductivity due to electrons and holes, the charge carriers which are actually moving, physically taking heat from one place to another place. And then the lattice thermal conductivity is another, because of the movement of phonons or movement, or you can say vibration of lattice. So this is given by 1 by 3 C, L, and V, where C is the specific heat at constant volume, and L is mean free path of phonon, and V is the average velocity, RMS velocity of the phonon. And for this L, which is the mean free path, it is determined by the phonon scattering, or sometimes in cases of phonon impurity scattering also. Then next is the electronic thermal conductivity. So electronic thermal conductivity is it can be given by L sigma T, and where L is Ne, this same can be given Ne mu Lt, where L is Lorentz vector, and which is 2.4 10 to the power 8 for free electron. The Lorentz vector for electrons in a single parabolic band and multi-parabolic band, and has to be determined carefully for the different materials. At high temperatures, due to excitations of electrons, the electrical, you can say Ke, it becomes large, and Ke can be extracted from the K total to determine the KL. So Ke, it is actually easy to, how do you calculate? It is, you can calculate Ke, you can calculate K total. Total thermal conductivity you can calculate, and electronic thermal conductivity you can calculate. And then if you want to calculate the lattice thermal conductivity, then you simply subtract from these to this, because actually calculating or measuring the KL is difficult. So that is the way it is done. Now, in order to select a good thermoelectric material, the optimum carrier density, how do we select, or how do we can say modify the materials to make it a good thermoelectric material? So one thing can be done, you can optimize the carrier density. What is the carrier density? as we saw, it is semiconductors carrier density. It can be electronic carrier density also. It can be hole carrier density. Very basically charge carrier density and number of electrons or number of holes present in per centimeter cube. So if it is a heavily doped semiconductor, as we saw in the second lecture, the 10 to the power 19 per centimeter cube is the carrier density. And for this, so you can optimize the carrier density by doping. You can change and start doing different measurements and then find out which carrier concentration gives you the best. And this has been arrived at 10 to the power 19 is the optimum carrier concentration. Now, next is the carrier concentration. Carrier concentration means number of electrons present in the conduction band or number of holes present in the valence band. Next important parameter is the band gap. So for a good thermoelectric material, the band gap should be typically equal to the, suppose you have an operating temperature TOP, then 10 KT. So if you have a material which with this band gap, it should be behaving in a best way. So one is carrier concentration about 10 to the power 19. Next is the band gap of the material should be 10 KT. Nearly 10 KT. So reasoning behind this 10 KT is that small gaps are generally good for thermoelectric performances as they lead to higher carrier mobility. However, if the band gap is too small, there is also problem. Then the thermal excitation of the minority carriers will adversely affect because electrons and holes carry heat in opposite direction. So electron, if the band gap is very low, even at that temperature, the electron will move from valence band to the conduction band with very, you can say, very small thermal excitations. Then electronegative difference is a measure of covalence of the bonding of the in the material. So suppose you are using two materials. In that case, if there is a large variation of electronegativity, then there is also a problem. So large electronegative difference indicates ionic bonding. You know from the basic chemistry. So then charge transfer and strong scattering of the electrons by optical photons. So these large scattering cause low carrier mobility, and therefore a good thermoelectric materials are composed of elements having small electronegative T difference and preferably should be having covalent bonds. Now, how to select good thermoelectric materials? Good thermoelectric materials will have a large average mass, as heavy atoms correspond to low thermal conductivity due to small acoustic phonons generated. And mass fluctuation scattering can be used to reduce the lattice thermal conductivity. This is and crystal structure with many atoms tend to have low lattice thermal conductivity. One argument is that the number of defects per unit tends to grow as the size of the cell increases. The bigger the size of the cell is there, then number of defects will increase. Crystal structure that has highly coordinated ions, it tends to have lower thermal conductivity, and that is it is an empirical relation. Now, if we just try to see for any material, suppose this is you have a any semiconducting material, and the carrier concentration you are trying to increase. This on x-axis there is a carrier concentration. So suppose for 10 to the power 17, 10 to the power 18, 10 to the power 19, 10 to the power 20, 20 to the power 21, and this way. So when you have a when you increase the carrier concentration, what happens? The electrical conductivity, electrical thermal conductivity, it increases because carriers are increasing, so thermal conductivity will increase. However, the lattice thermal conductivity remains constant. So this is thermal conductivity part. So thermal conductivity, lattice thermal conductivity, it doesn't depend much of the carrier concentration here in this particular case, and the electrical conductivity is increasing because more number of electrons or more number of holes, the carriers are injected, so they can take more current. So, so some of these will be like this. So this is the K part. Now there the sigma, the alpha part, the Seebeck coefficient, that increases like that follows this path. As you increase the carrier concentration from this side to this side, you can see that the Seebeck coefficient of the normal semiconductor follow this path. And the electrical conductivity, obviously, if more carriers are there, the electrical conductivity will increase. So this will also be following this path. So electrical conductivity is this. Sigma, sigma is this, alpha is this. Now, what is the numerator part is alpha square sigma. If you multiply this by this, you get a curve like this. And this curve, you need to divide with the K. So the jet to get the ZT value and multiplied by T. So if you by doing this, you will see the ZT, it follows a path like this. So the ZT value for with respect to carrier concentration is maximum at nearly 10 to the power 19 per centimeter cube. So that is the optimized carrier concentration. So good thermoelectric material, if a material is having this carrier concentration, okay, now carrier concentration is fixed. You have nearly 10 to the power 19 where you get good thermoelectric. Now, how this figure of merit that relates to the efficiency. Suppose figure of merit is 1. In that case, the temperature difference is 500 degrees centigrade between the hot end and cold end. So temperature difference is the difference between hot end and cold end. Suppose it is at 500 degrees centigrade, the temperature difference. Suppose one is at 500 degrees centigrade, another is at 0 degree, or one is at 600 degrees centigrade, another is 100 degrees centigrade. So in that case, you will get delta T 500 degrees centigrade. And if your material is having ZT1, in that case, you will find that efficiency of that thermoelectric material will be nearly 12 from here to here this way. So if you have, luckily, you find a material which is having very high ZT of 10, in that case, the same 500 temperature difference will give you an efficiency of nearly 35%. So you see how the ZT value, it affects your efficiency. If you have nearly 2, in that case, about 20%. If you have ZT value 5, you will get about nearly 30% efficiency thermoelectric devices. These are some typical materials which are very commonly used in thermoelectric devices. Usually the thermoelectric devices are optimized after doing a lot of experiments for 3 different temperature ranges: small temperature range, mid temperature range, and high temperature range. Where the temperature differences are or operating temperatures are higher. So normally this bismuth telluride kind of materials, they are used up to the temperature of 200 degrees centigrade. When the temperature goes higher, PBT and TAGS, they are used up to 500 degrees centigrade, where the ZT value is nearly 1. You can use at other like this material here also, but they are not, the ZT value is not very good during this thing. And similarly, at higher temperature, you can use silicon germanium alloy. This ZT value, if you see, like I said, for like bismuth telluride. So you have a bismuth telluride. So for bismuth telluride, if you see here, nearly at 200 degrees centigrade, it has a reasonable ZT value of 0.6. So if I use the same material at nearly 400 degrees centigrade, you see it will hardly work because the ZT value is very low. So similarly, if we see a lead telluride or TAGS material, so this at low temperature range, nearly 200 degrees centigrade, you have a very low ZT, but at higher temperature, you have a sufficiently high ZT value of nearly 1.2 at the temperature of 400 or 420 degrees centigrade. So TAGS, this material, and that PBT, this material, you use this material. This is having about 9 figure of 0.9 ZT at 400 degrees centigrade. So if you want your temperature range is, operating range is 400 degrees centigrade, you can see that PBT and TAGS are the best suited material. Similarly, by following this, if you want to make a device which is having an operating temperature of 1000 degrees centigrade, you can see there are only two materials, though this material is having high ZT, but it has several other issues. So you need you use silicon germanium alloy, which is having a ZT of nearly 0.9, and here also. So N type and P type silicon. Now, what are the we see what are required? You require high alpha and sigma and low K. So is there any way by which you can actually reduce the K value or thermal conductivity values? So can be done by doing some manipulation. So ideally, if without manipulation, if you have a material which is having high electrical conductivity, it is going to have high thermal conductivity because both of them are related to each other. But so metals have a very high sigma but have very low alpha. The Seebeck coefficient is very low, and these are having very high thermal conductivity also. On the other hand, if you see glasses which has very low thermal conductivity and very low electrical conductivity also. So both these are as expected. If you have lower thermal conductivity, electrical conductivity is going to be low. Similar case, if you have higher thermal conductivity, the electrical conductivity is expected to be high. So what we want a conductivity, a higher conductivity of metal, but at the same time, low conductivity, low thermal conductivity like glass. So we will, how we can do it? So a concept was proposed for the materials which shows low K as in glass, but high sigma as in well-ordered crystals. This is called as PGCE or phonon glass electron crystals. To control these properties at will, suppose whatever we want the property to be controlled in that way. It is very difficult, as I already said, because two of these conductivities are interrelated. So this problem is how it is tackled. It is tackled in in two different fronts. Synthesis of new materials in solid solutions. Solid solutions means where one solid matrix and another solid matrix, they are you can say synthesized together. And this kind of solid solution have a very complex crystal structures. And because of that, they possess low thermal conductivity. And another way is that you do nanostructuring. You make a very fine powders and those materials, and then uh, uh, just making nanostructuring, it will enhance the ZT value. So the idea is lower structured, uh, 0D, 1D or 2D materials. They show high electrical properties as reported in the bulk. So these were the strategies which were actually has been practiced over last so many decades. Initially, uh, the idea is actually to reduce the thermal conductivity and maintaining the electrical conductivity at the same value. Or you can say you reduce the you reduce the thermal conductivity more, but at the same time there should be less effect or less reduction in the electrical conductivity. That will also help. So in the first generation materials where ZT was would be successfully achieved of the order of 1, the the general strategy was the point defect scattering, means you the addition of point defects inside the matrix. And another was the optimizing of the carrier concentration. So carrier concentration you can change, and then you add the point defects in the inside the material matrix. So this was initially in the first generation materials, this was done. Then after some time, the nanostructuring, as I said, nanostructuring was a lot of research was done on the nanostructuring. It has also yielded some good results, and with that nanostructuring, one could achieve the ZT value up to 1.3 to 1.7. Now, in now the present generation, where the ZT had exceeded 2, so there are we can say introduction of mesoscale structuring, where this introduction, that is the main purpose is to reduce the thermal conductivity, and also doping induced electronic structure modification. You specifically of certain dopings you can select with the dopants with the electronic structure calculations, and then you can optimize the electronic structure, and with this doping you can modify the electronic structure, and then you can actually implement by making the material after those calculations. Then this matrix precipitate band alignment for reducing the thermal conductivity. So some of these, like introduce point defects. For example, bismuth telluride has lattice conductivity is 2.4 watt per meter K, and ZT value is 0.6. Bismuth antimony telluride, and this when you add the doping, then the lattice K lattice becomes 1.5 watt per meter K, and ZT becomes 1. So by you see just introducing the point effects, it has changed both the K and ZT values. And then increase the lattice period, where you can select the larger unit parameters. And so if you have a cell which is having larger parameters A, B, C values, so it is actually elongated lattice. So obviously, because length has increased, so the mean free path, or you can say it will provide a short mean free path length. By using boundary scattering, material grind, then make pellets using hot pressing. So what is done? You grind the material to a very fine powder, and then press it and make pellets, and that those pellets are made at very high temperature, or not very high temperature, but at high temperature, so that it can have high density, or in same way by nanostructuring also. So to summarize, the most commonly used materials for this generator is lead telluride. Lead telluride is compound made of lead and tellurium having small amount of bismuth or sodium. This is done for the making them pure N type materials. The other compounds used for making thermoelectric power generators are this is tags, bismuth telluride, bismuth sulfide, germanium telluride, zinc antimonide, zinc telluride, and indium arsenide. There are several materials. These are the common materials. And what are the main applications of thermoelectric generator? For increasing the fuel efficiency of car, thermoelectric generators are used. These generators use heat produced when the vehicle is running. So in a car, when your engine is at a very high temperature, you place some thermoelectric generator there, so that the heat which is otherwise would have been on waste, this can be converted into electricity, and so the efficiency is used. This electricity can be used for other things. Similarly, in like bikes also, you have a silencer where the temperature is very high, or near the engine actually, you put thermoelectric generators, and a lot of, because temperature difference is very high there, so a lot of energy is generated. Yeah. Then this is also the most you can say usefulness is that when you have a deep space missions where sun is also not there. There's no light from sun. Suppose in like in space, which is in our solar system, you can use solar cells where the power is generated using the solar cells. However, if you are having some deep space missions, in those places there is no sun. So what you can do there to get the power is use thermoelectric generators. So you put some radioactive source of very high energy, which is continuously decaying and generating heat, and with that heat in adjacent to that heat source, you place a thermoelectric generator, and that power can be utilized in those missions. So, and these generators are used to supply powers to remote stations also, where the temperature difference is very high. Suppose solar cells are also used in remote stations, and thermoelectric power can also be used. But only thing is that for using thermoelectric generators effectively, the temperature difference should be as high as possible. More the temperature difference, you will have more the powers. What are the advantages? So advantages of thermoelectric generators are this: as an alternative source of energy for special applications such as deep space missions, remote inaccessible locations, and they require obviously no maintenance, because a material generally works for a very long period of time. And harvesting heat emitted by human body, instruments, automobile industries, impact on global warming is very less. So even our temperature, body temperature is 33 degrees centigrade. So suppose this heat can also be utilized to get the this to generate the power. And there are certain limitations also. One is high output resistance is required, because these are normally high current devices, high current and low voltage devices. So for getting high output voltage and power, several thermoelectric generators are connected in series, which in turn increases the total output resistance. So as you go on increasing the number of devices, the output resistance is bound to increase. Therefore, for transferring high power efficiency, large resistances are needed because you need to have an impedance matching to have an efficient power transfer. And thermoelectric power generators generate less electric power for the same heat flow. That is, they have low efficiency as compared to the other mechanical generators. Then low thermal characteristics. The heat dissipation of any device depends upon its thermal conductivity, and any good thermoelectric power generator has low thermal conductivity and hence poor heat dissipation. So these generators are efficient only when small power is required. They have actually very low voltage in somewhere in the millivolts only. It generated by unless you convert it using the voltage converters. Then thermoelectric generators are costly as compared to other generators. Now let us see what is Peltier effect. We saw Seebeck effect. Seebeck effect, what was the Seebeck effect? When you put, suppose you have two junctions, one is at higher temperature, another is at low temperature. And in that case, if you, their EMF is generated. So if I try to do something like there is no temperature difference, but if I try to pass the current through it, or I put those two junctions at different potentials. So if I put those two junctions at different potential, the current will flow. So because of the current will flow, the heat will be actually transported from one junction to the another junction. So we can say this in other way that at one junction heat will be evolved, at another junction the heat will be absorbed. So this is Peltier effect, and it is opposite to it's just opposite to the Seebeck effect. So if two dissimilar materials are joined together at both ends and current is flown, then at one end the heat energy gets rejected, and in another end the heat energy gets absorbed. So it is opposite to Seebeck effect. If the charge carriers are going from low Fermi, here if you can see the charge carriers are going from low Fermi energy level side to the high side, then they require energy will be supplied by the lattice. So if lattice supply the energy, what will happen? Obviously, it will get cooled. And similarly, for the higher energy, it will get heat. So this is the Peltier heat, and this is the Peltier coefficient. So Peltier device will become just like you are trying to pass the current inside the a P type N type junction, and then so it will become now a reverse. So it will be the cooled junction because the heat has been transported from that side to the other side where it has been actually dissipated. Now there is another effect which is related to the thermoelectric is the Thompson effect. So suppose when a current is passed through a conductor or semiconductor which is already having a temperature gradient. You have a suppose you have a conductor, and one end is at very high temperature, another end is at a very low temperature, and then you try to pass the current. Just understand in this way. So then heat is either evolved or absorbed. So in this also, either the heat will either it will be evolved or it will be absorbed, and this process or this phenomena is called as the Thomson effect. What is Thomson effect? If you have a semiconductor or a metal which is having a temperature gradient, means one end is at higher temperature, another end is at lower temperature, and if you try to pass the current, then what will happen? Either heat will be absorbed or heat will be evolved. So this is Thomson effect. So if 2 points in a conductor are at different temperature, why it happens? The density of electrons at these points will differ, and due to this, there will be a potential difference between these points. So, like in our initial first explanation, where the temperature, if temperature was increased, the electrons were moving from one side to another side. So, if temperatures, so suppose you have a this metal where one part is hot. So this is hot. So there are the electrons which were initially there. Initially there were equal number of electrons, electron density, equal electron density. So equal number of electrons per square centimeter or per square centimeter cube. Then if the temperature is increased, in that case, those have moved from this side to this side. So if you see now in this side you have more electrons, and here at this side you have less electron. So you will have an EMF across these. And now if you try to pass the current from this side to this side, what will happen? The electrons which are moving from this side to this side have to face this potential also. One is the external field which you have put, because you must have applied some voltage, because of that current is flowing, and another is this potential which is inside this, which is being generated because of the movement of the carriers from one side to another side. So so if the current is passed through a copper bar, suppose which is like here, so this is suppose a copper bar AB. If current is passed, and this is suppose we have heated this bar at the center. So now you will have a temperature gradient. This side it will be like this. So temperature here it is less, it is increasing, and then it is again decreasing, because we are actually heating it at the center only. So it indicates that heat now from here to here, the heat will be absorbed, because what happens here at this point, C point, it is having less potential. So this C, sorry, as compared to this A, it will be actually at a higher potential. So this indicates that heat is absorbed along AC and evolved along CB. So from here to here, heat will be absorbed. From here to here, it will be evolved. Thus, heat is transferred due to the current flow in the direction of the current. This is called as the positive Thomson effect. Suppose heat is transferred in the opposite to the direction of flow of the current, then it is called as the negative. Then it will be called as the negative Thomson effect. Copper, silver, zinc, and cadmium shows the positive Thomson effect. So the thermoelectric effect is the direct conversion of temperature difference to an electric voltage, or vice versa. In case of Peltier devices, traditionally the term thermoelectric effect or thermoelectricity encompasses three separate effects. These are Seebeck effect. What is that? If you have potential difference, temperature difference, and EMF is generated. The Peltier effect, if you apply potential difference, the temperature difference will be created. And Thomson effect, where if you have a temperature gradient and passing the electrical current, then in that case it will be either evolved or absorbed. So these just always remember these three effects. The Peltier and Seebeck effects are most basic of these three, and are essentially the inverse of one another. For which reason the thermoelectric effect may also be called as the Peltier-Seebeck effect. Joule heating. What is Joule heating? Suppose you start passing a current through a resistance. In that case, the I square R upon 4.2 Joule amount of heat is liberated. This is not actually the thermoelectric effect, though it looks like. So this Joule heating is not actually a thermoelectric effect. Thermoelectric effect is where the uh, between two dissimilar material uh, where the temperature difference is generated because uh, of applying voltage, or because you have created a temperature difference, due to this a voltage is generated. So they are, though they are somewhat related, but they are not similar. In Peltier, Seebeck and Thompson effects, these are reversible. However, Joule heating is not reversible. A thermoelectric device creates a voltage where there is a difference of temperature on each side, and when a voltage is applied to it, it creates a temperature difference. It's a similar thing. I have written it just in another way, and this can be used to generate electricity, to measure temperature, or to cool objects, or to heat them. So these are to measure temperature, thermocouples are based on this principle. There are several Peltier coolers are available in the market, where you pass the current and then temperature is reduced. And I have seen up to minus 80, minus 90 degree centigrade can be easily achieved by just passing the current. Or obviously you can heat also. So if you see the present status of thermoelectric, if I see both inorganic semiconductors and organic semiconductor also. So for the majority of the work is being done, as I said, by enhancing ZT values, and they are mostly by reducing the thermal conductivity only. There's no way you can go on increasing the electrical conductivity by keeping the thermal conductivity constant. So most of the people are doing the work where they are reducing the thermal conductivity. So at this highest ZT in segmented devices or bulk devices is nearly 2.2 at 900 Kelvin for this material, that is the telluride, and which is having strontium telluride. So for this thing, this is and efficiency nearly 12% has been achieved in the segmented devices, which are consisting of cobalt antimonide and bismuth telluride based thermoelectrics. In the emerging thermoelectric, that is the organic based semiconductors where we are using. The advantages that these are flexible devices, but the issues of concern are these are having very poor ZTs in organic materials. I'm talking about. Yes, and they are lack of stable high conductivity and type materials. And highest ZT in organic materials is reported around 0.42. This is at room temperature, and the material is P type P dot PSS. P dot PSS is the same material which we saw yesterday. It is being used as a whole transport material in organic solar cells. So the same material, which is a semiconductor, is used in the using the thermoelectric devices also. So in BRC also, we have a group who is working on thermoelectric power generator in our division, and we have developed these thermoelectric generators, and for three different temperature range: low temperature range, mid temperature range, and high temperature range. And the efficiency, these are the you can say compound which we are using. that is the bismuth telluride based only, bismuth telluride based only. These are different dopants, and this is the structure. 300 degrees centigrade is the low temperature range, and the cool end is at 40 degrees centigrade. And so typical efficiency achieved in this device is about 6%. For mid temperature range, 300 to 500, these are the compounds, and the temperature difference is about 420 degrees centigrade, and the efficiency is about 6%. For segmented, like for higher temperatures, for like high temperature range, this is segmented means you have now two different segments. One is for high temperature, another is for low temperature. So this is the same. You have this leg, and below that you have put this leg. So let us consider this is suppose 500, and this is a 33. So this part, which is having an efficiency of 6% at nearly and mid temperature range is about 500, and then this is at the lower temperature. So this is segmented lag, not high temperature. High temperature I have not placed here. That is the height for high temperature range. We are using silicon germanium alloys. In like this was for thermoelectric. If I say for the solar cells, the best solar cell efficiencies, this was actually left yesterday. Single crystalline silicon 27.6, gallium arsenide 32.9, polycrystalline silicon is 23.3. So this is the best efficiencies for the solar cells, and this is the efficiencies for the thermoelectric. So you can see for a 4-junction multi-junction device with concentrators of nearly 400 sun, 47.1% efficiency has been achieved. And this is the conversion efficiency for different solar cells when they are actually used in the modules. So we have solar cells for suppose in modules you are using silicon semiconductors, then crystalline and non-crystalline, and non-crystalline is this crystalline is single crystalline, polycrystalline. So the modules are available from 10 to 17% in the market. For polycrystalline, 9 to 13%. For amorphous, actually it is even less than somewhere 4% to 10%. For compound semiconductors, it is 18 to 30%. Organic semiconductors, some modules are available, but their long-term stability is not yet proven. So, but efficiency is nearly 7 to 8%, and 2 to 3% for the organic bulk heterojunctions. And this is the latest for different solar cells. On this you can achieve, you can get from enough. So with this we have covered thermoelectric power generators and solar cells, and we also studied semiconductor physics that was also completed in the first part. So now we come to the part 3, which is though all these materials, whatever we have studied, are device-worthy materials. So as per the syllabus, they are important elemental and compound semiconductors, which are germanium, silicon, tellurium, second, sixth, third, fifth, and fourth, sixth compound semiconductors, and amorphous silicon. And the other part which is left is the single crystal growth and growth techniques. Methods are like Chakrovsky method, Ford Zone method, and other crystal growth methods, hydrothermal growth methods, crystal growth for silicon and gallium arsenide, production process of wafers, growth of quartz. So this is these are the semiconductors. These are the methods which are very commonly used for the making single crystals, growing single crystals. And then there is another another method of making single crystal in 2D format or a thin film format. So for that, the thin film deposition techniques, thermal and electron gun evaporation, DC, and our sputtering epitaxial film deposition techniques, CVD, PP, LP, and the. So this part is so. So let us start with the important elemental and compound semiconductors. I will quickly go through this. Just this one. I will come. Sorry. So the elemental and compound semiconductor, the important elemental is as we see in the first few classes also, silicon and germanium are the most important elemental semiconductors. And the fourth group compound semiconductor is silicon carbide. If we see fourth, sixth compounds, lead sulfide, lead selenide, lead telluride, these are the important compounds, semiconductor. So let us see the elemental semiconductor, silicon. Silicon is a very the most common material used in the semiconductor industry. It has a melting point of 1414 degrees centigrade, and if you go on increasing the temperature, it boils at 3265 degrees centigrade. The density is 2.32 gram per centimeter cube, and it it crystallize in the diamond structure. That is, what is diamond structure? That is FCC structure, and in fact, two FCC structures interpenetrating by each other by diagonally interpenetrating at 1/4, 1/4, 1/4 A, where A is the lattice parameter of that cubic structure. Thermal conductivity is 149 watt per meter K, and the electrical resistivity is you see it's having reasonable resistivity, so 2.3 10 to the power 3 ohm meter, and band gap is 1.12 electron volt at 300 Kelvin, and thermal expansion is 2.6 micrometer per millikelvin. This is millikelvin. And how it is produced? So silicon, mostly silicon is silicon is produced using from the earth crust only. So up to 99% purity is made by reducing sand with highly pure coke. So you have silica, which is from the sand, and then it is reduced with the very high purity coke at higher temperature. So this reduction is carried out in an electric arc furnace, and so the remaining excess SiO2 is used to stop accumulation of silicon carbide. So SiO2 then it reacts with the carbon and silicon, and then 2CO. This SiC is then it reacts with the SiO2, and then what happens? The silicon is produced, and then more silicon carbide. In this process, silicon and silicon carbide are produced, and that silicon carbide is further reduced to the silicon. This was the most common method for making the silicon. Germanium is another important elemental semiconductor, which having slightly lower melting point of 937. The boiling point is 2830. Band gap is, if you see, as compared to silicon, it is very low, so 0.67 electron volt. So at room temperature, uh, there are a lot of electrons which goes from valence band to the conduction band, even if it is an intrinsic germanium, and therefore the devices which are based on the germanium are either has to be cooled to a low temperature, or otherwise they will have a lot of noise. The resistivity is about 1 ohm meter. Crystal structure is same as of silicon. It is FCC. In place of silicon, you just place germanium. And density is 5.3, slightly more than the silicon. And thermal expansion is about 6 micrometer per millikelvin. And thermal conductivity is 60.2 watt per meter K. It's a very widely used semiconductor. It reacts with oxygen at higher temperature and then makes GO2. The physical properties are it's a bright, shiny, brittle. And chemical properties are it is inactive, does not dissolve with water or react with the oxygen at room temperature. These are some properties. And it is produced mainly from the sphalerite, which is actually an ore of germanium and zinc, the sulfide ore, you can say. And it is also found in the silver, lead, and copper ores. Another source of germanium is fly ash of power plants fueled from the coal, uh, and that deposits that contain germanium. Then third is the amorphous silicon. Amorphous silicon is actually very important. It is a non-crystalline form of silicon, and which is used in the thin film technology and LCD and solar cells. In amorphous silicon, not all the atoms are fold coordinated like in the crystal. Every silicon atom is tetrahedrally coordinated with the another silicon atom. However, in amorphous, there are several bonds which are not actually saturated. And there is no long range order also, like it was in single crystals. So atoms obviously will be having dangling bonds, and these are the defects. And because of these defects, there will be a lot of anomalous electrical behavior can be observed. These, as told you yesterday also, in case of amorphous silicon solar cell, the dangling bond problem and like unsaturated bonds are this problem is tried to resolve by passivating the silicon by hydrogen, and it makes a bond with the dangling. And and reduce their density, the dangling bond density, and therefore then can be used. So such obtained hydrogenated amorphous silicon has a sufficiently low amount of defects, and it can be used to make devices such as solar photovoltaic cells. So yesterday, it is used as a solar cell material with a varying and wider band gap up to 1.9 electron volt. The absorption coefficient of amorphous hydrogenated silicon is very high as compared to silicon. Silicon, it was 1.1 electron volt or 1.12. Here you can go up to 1.9 electron volt also. So the band gap is really high. It can be deposited by sputtering also, CVD or plasma enhanced CVD, and can be deposited on a variety of substrates such as plastic, metals, and therefore very useful in different type of device fabrication. So when you want to deposit a amorphous silicon, you have to just sputter it. or by thermal evaporator also. Thermal evaporation is slightly difficult because temperature is quite high to achieve, but it can be easily done by sputtering process. Now, let us see fifth, four, six compounds. Some of the important compounds are lead sulfide, lead selenide, and lead telluride. These are some important compound semiconductors of 4,6 group. These compounds are characterized by narrow energy gap. So energy gap is low in these, and carrier mobilities are high, and dielectric constants are also high. And the energy gap is, band gap is very low, as I already told. It is nearly 0.3 to 0.5 electron volt. And the unique features of direct energy gap, in like germanium also we have indirect energy gap. In silicon also we have indirect energy gap. But in this fifth, in this 4,6 compounds, the band gap is direct energy gap. Direct energy band gap materials are very useful in uh, the optical materials, for the optical property, optical devices. The energy gap also increases with the if you increase the temperature. So these have a positive temperature coefficient. The main applications of these compounds are in light emitting devices, diode lasers, and detectors in the infrared spectral region. See, all these direct band gap materials are very useful for the lighting application, lighting where light is either emitted or being absorbed directly. And if we see some 3,5 compounds, so the important compounds in 3,5 are when you met three in one compound is okay, one component is from group 3, and like aluminum, gallium, indium, and one component is from group 5, which is nitrogen, phosphorus, arsenic, antimony. If you combine these in a you can say different permutation combination, the compound which you get is the 3,5 compound. So it in all, if you see, this will give you a total 12 prospective combinations, and the most important one, 3,5 compounds are gallium arsenide, indium phosphide, gallium phosphide, and gallium nitride. 10 commonly used compounds are I will show in the next slide. And all of these third, fifth combinations, these crystallize either in the diamond structure, like silicon and germanium, or in the zinc blende structure. So how you will differentiate whether it is a zinc blende structure or diamond structure? If the compound is same, if both the atoms are the same size, then this will be diamond. If there is a lot of difference between these two, then this is zinc blende structure. And there is another structure which I did not cover in the second lecture, that is a wood jade structure. As we saw for FCC structure, FCC is a closed pack structure. Similarly, there is another closed pack structure, which is the hexagonal closed pack structure. So in hexagonal closed pack structure also, you get the similar kind of voids. So just remove an FCC with the HCP, and when you put another in a compound semiconductor, if you put the same second, you can say element at the void of voids in the HCP structure, then whatever structure will be formed, it will be a wood joint structure. So wood joint structure is nothing but it is actually a HCP structure where you have made a compound semiconductor. One element is at HCP, all the HCP sites, and another element is at the you can say voids formed under these HCP side. So these are the important 3-5 compounds. These are aluminum phosphide, aluminum arsenide, aluminum antimonide, gallium nitride, gallium phosphide, gallium arsenide, gallium antimonide, indium phosphide, indium arsenide, and indium antimonide. Similarly, if we try to see important second 6 compounds, see if you see second 6 means they have two electrons in the outer orbit. 6 means they are less of 2 electrons. So these 2 electrons they go to the 6 means these 2 electrons are taken by the other element, and effectively you have 0 electron, or very in ideal situation you will have 0 electron. So the compounds which are very common or most commonly used as a semiconductor, these are zinc oxide, zinc sulfide, zinc selenide, zinc telluride, cadmium sulfide, cadmium selenide, cadmium telluride. This is second, this is sixth. So you just transfer 2 electrons from these to this, and then you can make different compounds. So all the 7 second 6 materials have a wider band gap ranging between 1.5 to 3.6 electron volt. So here the band gap is relatively high, and the common applications for these 2-6 elements here are like LEDs and signal processing also in many cases. The growth methods vary by materials, but mostly grown by melt growth. Zinc oxide cannot be grown by melt growth. Similarly, zinc sulfide also, there are some other issues with these materials. And these methods can be grown by epitaxial methods also. So advantages are, these are less energy loss, more efficient, and potential for low cost, and higher breakdown voltages, higher power and frequency applications. Because these are having higher breakdown voltage, that is the reason why these can be easily used at a higher power and frequency applications. And since the concentration is can be achieved with a high, it can be prepared with a high doping concentration, thinner device layers are sufficient. And then high energy, high electron mobility are exist there in these semiconductors, and therefore the operation is very fast. So faster device operation is this. So now let us see another important material, which is tellurium. The melting point of tellurium is 449. Boiling point is nearly 988 degrees centigrade. The band gap is very low, 0.38 electron volt. The resistivity is also very less. Density is 6.2. Thermal conductivity is also very less, 3.3 watt per meter K. The thermal expansion is 18 micrometer per millikelvin. And atomic number is 12. The crystal structure is trigonal. This is trigonal structure is what? You have a cubic. Suppose you just hold it the diagonal phases and just extract it. So in that case, you will have all ABC will be equal, alpha, beta, gamma will be equal, but not equal to 90 degrees. This structure is trigonal, and tellurium crystallized in this structure. What is importance? Because of its low electronegative negativity, tellurium form a variety of materials with small band gaps and find applications in photoconducting materials, solar cells, infrared detectors. And most of the tellurium is obtained from copper deposits, where it occurs in very trace amount. then it can be. Then let us see some of the ternary and quaternary compounds, which are these are also used in some very high-end devices or sophisticated devices. The aluminium indium arsenide, gallium arsenic phosphide, gallium indium nitride, gallium indium arsenide, gallium indium phosphide, aluminium gallium arsenic antimonide, gallium indium arsenic phosphide, and aluminium indium arsenide. So if you see, suppose it's a gallium arsenide, I will just try to explain one. In this, you dope the indium, you put indium inside that. So what it will do? Certain gallium will be replaced by indium. So you will see, suppose I say 50-50. Suppose I have added gallium arsenide and indium arsenide 50-50. So on all the 50% of the gallium sites, indium will occupy. And so the composition will become gallium 0.5, indium 0.5, and arsenide. So the similar is for all these cases where a fractional compound or fractional you can say element replaces the element replaces in fraction of the sites. So with this, I think with this I finish today's lecture. And if you have any doubt or any question you need to ask, I'm ready to answer those. And tomorrow or in the next lecture, you will see the crystal growth, out of the how these crystals are grown for these materials, different crystal growth methods, and thin film deposition methods. So if there are no questions, then let us close the lecture. See you on Friday. Bye.